So section 4.1, definitions and examples. Throughout the whole chapter, U, V, and W will denote vector spaces over the field F, but actually most of the time this scalar field F will be the real numbers or sometimes maybe the complex numbers. We will work with linear transformations. But first of all, we should clarify these different names that the book uses. So we have this function notation T mapping from U into V. Usually this is how we say it, the two maps from U into V. We call this sometimes function. This is mostly used when we have mapping from the real numbers into real numbers, like what we had in calculus. So T is called, in this case, a function. The map is used usually when U is a set and V is a set. So just mappings between sets. And when we have vector spaces, then usually we use the name transformation. So most of the time I will use the name transformation in this case. So the definition, T mapping from, and we don't say transforming from, we say mapping from U into V is called a linear transformation if T satisfies the following two properties. First property, T U plus V equals to T of U plus T of V for all UV from the vector space U. We can apply T term by term. Second property, T A times U equals to A times T of U for all A scalar from the scalar field F and for all U vector from the vector space U. Which means that we can factor out the scalar. So if you think this reminds you something, yes, it should remind you to the properties of vector space. Interesting thing here is that we usually combine these two properties into one. For the vector space, we could have done it actually, but in those cases when we had to show that a set is a vector space, it was more convenient to check the two properties separately than together, especially if we needed to find a counterexample. So now the combination of the two properties is that T from U into V is linear if and only if T A times U, and now let me emphasize which one is the vector, plus B times V equals to A times T U times B times T of V. So again we can apply T term by term and also factor out the scalars. Let me show the steps of the proof just to practice proofs. Just showing the identity between the two. Let me call this 3. So 1 and 2 implies 3. So we want to show that 3 is true using 1 and 2. That means we start with the left hand side of 3. So T of AU plus PV. So these are vectors. And according to 1, we can separately apply T on AU and the second vector BV. So we use the first property with U replaced with AU and V replaced with PV. Then we apply twice the second property. So the second property says that we can factor out scalar. Now we have two scalars, A can be factored out and B can be factored out for all AB from the scalar field and for all u v vectors from u vector space. All right, so this first part shows that if I use 1 and 2, then I can get 3. Then the other way to get from 3, 1 and 2. So I'm going to use 3 now. 1 is when you have just u and v. So 3 holds for all AB. Let's take A equals B equals the unit 1. So that means I have for T u plus v. This is really 1 times u plus 1 times v. And then I can apply 3 to get 1 times t of u plus 1 times t of v. And of course the scalar multiplication by 1 doesn't change the vector, so I'm left with t of u plus t of v. And then to have the second property, for the second property I don't have a second vector v, but 3 has a second vector. So the third one can be used if I introduce a 0 vector, for example in the form of a 0 times the 0 vector. This is overdoing it, since if one of them is 0, then it's already the 0 vector. So then this is the same as AU, what I'm supposed to be using for the second property. I'm supposed to have T of AU. AU is the same as AU plus the 0 vector. And now I can use the third property. That says that I can do it entry by entry, term by term, and I can factor out the scalar. And since the scalar I factor out from the second term is the 0 vector or 0 scalar, that cancels the second term. So I'm left with a times t of u, which is exactly the second property. The first and second property implies the third one, and the third implies the first and second. Because we do a lot of calculations with these linear transformations, linear functions, it turns out that many times it's more convenient to use this combined, shorter way of writing it. So we have to now look at a bunch of examples. I would start with the identity map. So the identity map is from one vector space u into itself u. So in this case v equals to u. The second vector space is the same as the first. And we define it by saying that I of u should be equal to u for all u vector from the vector space u. So we have to check that this is linear. Yeah, we can use for that the third property. So we use for all AB from the scalar field for all u v vectors from the u vector space. We have to check what happens to the image. Now the transformation is this I transformation, the identity map. What is the image under this map, under this transformation of AU plus BV? So the definition is that you just leave whatever the argument was, it doesn't change. So that means this is A times U plus B times B. Now we have to compare this to the right-hand side of the third properties. So the third property says that you can have separately A times the transformation of U plus B times the transformation of V. So if you check what that is, A times the transformation of U plus B times the transformation of V. So again, the definition of The identity map is that it leaves the vector alone, so that means that this will be AU plus PV. And then you just compare the two parts and you get that this is exactly the third property, because it says that you can separate the application of this identity map for terms. Term by term can be applied, and you can factor out the scalar. Another simple example is the zero map, denoted simply by a boldface 0. So this is a zero map. It can go between arbitrary vector spaces U and V. We don't need a restriction like for the identity map that it goes from U into U. And the definition is that if you apply this to any vector U, you get the zero vector of the second vector space V. And this is for all U in the vector space U. So to check linearity, again we check the two sides of 3. Left hand side of 3 is that we have AU plus BV. This is one vector, so we don't have to do much work with this right now, because it says that for any vector you get the zero vector, so then this also supposed to give you the zero vector. Then we check the right hand side of 3, so this is the left hand side. The right hand side is A, and then the transformation U plus B times the transformation of V. Now for these parts, the transformation gives us the zero vector always. So what we get is A times U plus A times 0 plus B times 0 vector. And then we had this very important observation at the beginning, that when you multiply the zero vector, you are left with the zero vector. And when you add together zero vectors, you get the zero vector. So we get with this simplified version of the right hand side of the third property. And now we compare the left hand side with the right hand side, and we see that they are equal. So that means the third property holds, and we have a linear map, linear transformation. Let's go now to more abstract vector spaces. The derivative usually is denoted by D, capital D, when we talk about maps. So this is the derivative. Actually, this is called operator when we have U, V, special vector spaces that are actually function spaces. But these are also vector spaces, so we keep using the name transformation. I just want to mention now that we have now several different names for the same thing: function, map, transformation, operator. It depends on between what kind of things these maps are going. So the derivative can be a lot of different things. We looked at the vector space of polynomials, for example. So we can have this from F, the vector space of polynomials with real coefficients and real variable, into the same space. And then what we have there is that the general vector can be written as a polynomial p of x with some coefficients. So you might want to index them: a0 plus a1x plus a2x squared. It's supposed to stop at some point, but we don't know when it stops, so in general we use the n for the nth degree polynomial. So this is a typical vector that we can use for a polynomial. So instead of u vector now we use a different notation, but it represents an element of a vector space. And then what we have is that d applied to this u vector means the differentiation of the polynomial, and the way we differentiate term by term, that already kind of indicates that this is linear, and you can factor out the constant multiplier. So that means this will be a1 plus 2a2x plus, and so on, n times an x to the n minus 1, using the power rules. So you see that these are also, these coefficients are again numbers, real numbers. We have powers, so it fits the definition that this is a polynomial. Now if you want to check the linearity, well, it's kind of tedious if you want to have two different vectors, u and v, then you're supposed to write out two general polynomials with some general powers n and m, and then two different notations for its coefficients. So this is a little bit tedious. For example, if u is a0 plus a1x plus an xn, and then v is b0 plus b1 x. We cannot assume that they are of the same power, so we have to use bm xm. Then the question is which one is larger power. Typically what we say is that without loss of generality, let's assume that m is larger than n, or maybe equal to it. So these are two general vectors in this vector space of polynomials. And then we're supposed to examine what happens when you apply a times u, you differentiate a times u plus b times v. But the thing is that already when we differentiated one polynomial, we use the fact that we have constant multipliers and we have term-by-term differentiation. So I don't really want to write down this proof, especially because it is a question of definition, whether now for the derivative of a polynomial, is this the definition or is this coming out from the power rule? And then we also had the sum rule and the constant multiplier rule in calculus 1. So I don't want to say that this should be the definition of the derivative because then it's confusing. We really have a definition for the derivative from calculus 1 and there is nothing wrong with that. And already in calculus 1, or for example in real analysis, actually you're supposed to really see it and derive these properties. Which means that if you have a function, typically this was used separately, that if you have two functions, f of x and g of x, then you differentiate term by term. And if you have constant multiplier, that can be factored out from the derivative. So this is actually property 1 of the linearity, and this is property 2 of linearity. And it's much nicer actually to refer back to calculus 1 and real analysis to say that because of these properties, this is a linear transformation. Especially because this is actually true not just for polynomials, this is true for all differentiable functions. Yeah? So for example, we could have also sine of x function, the trigonometric functions, the exponential functions, and so on. In fact, let me mention that another popular function space, a vector space of functions, is when you have sine of x, cosine of x, then for example sine of 2x, cosine of 2x, sine of nx, cosine of nx, and then these are functions 2n, and then you can look at the span of this list of functions where n is a given number, and for example x could go between 0 and let's say 2 pi to have periodicity. So we could show that of course this is a vector space, and if you denote this with u, then the differentiation also go from u into u. For example, these sine cosine functions are used a lot in numerical approximations. And this is also a linear transformation. I even mentioned before the space of continuous functions. So now if I use C1 notation, for example, C1R denotes the once continuously differentiable functions, or simply continuously differentiable functions. So this is a vector space. Why? Because if you add together two functions, then the new function is differentiable continuously. And when you scalar multiply a function, it's also differentiable continuously. How do we know that? That's because the differentiation is, again, in general, a linear operation. So for that reason, the sum is also differentiable, and the derivative, more precisely, equals to the sum of the derivatives. So actually, we know that it's vector space, but we know also more than that. We know that the derivative goes from differentiable functions over the whole real line into, well, after differentiation, what you know is that you get continuous functions at least over the whole line. So that means that the argument x can be any real number, and we get a linear transformation. What's not obvious, and we're not going to talk about it right now, what would span this C1 vector space? Many times we don't work with the whole real number line, especially in numerical calculations. You cannot go to infinity with x. So R is the interval from -infinity to infinity. I usually don't like to work in my research with the whole number line and to have so-called Cauchy problems. So instead of that, mostly we restrict the argument x to an interval, for example, 0, 1. So these are the continuously differentiable functions. Generally, we denote it with f of x with argument x in the interval 0, 1. And again, what we have is that the differentiation from this vector space goes into continuous functions. That's what continuously differentiable means. And this is also linear. Other examples, so this is a big thing, of course, to do differentiation. Other examples, is the opposite of differentiation is integration. So we can have definite or indefinite integral. For indefinite integral, we have this plus c problem that might cause some confusion. Let's just consider definite integral with a specific interval from, for example, 0 to 1, f of x dx. So this is supposed to be a number after integration. That means that what we can see here is that the integral operator, this is actually mapping from L1, I used this before, the space of integrable functions over the interval 0, 1, and it maps into R. And now I have an additional name to an operator like that. So this is a function space. Since we have functions in it, it's a vector space, and these are scalars. So this is a scalar field. When you have a map like that, going from a function space into a scalar field, this is called a functional. Still, it's a form of mapping, and it's a linear transformation also. Why is it a linear transformation? Because again, from calculus 1, what we learned is that when you integrate from 0 to 1, f of x plus g of x, you can do it term by term. And when, so this is the first property, and when you have a scalar multiple of the function that you integrate, you can factor out this scalar multiplier. So this is true for all c from the real numbers, and also for all f that is integrable. So this means that it's a linear transformation. It is also possible to consider the indefinite integral, for example, from the vector space of polynomials into the vector space of polynomials. But then one might have to restrict the constant of integration, as I mentioned. So the power rule is, of course, that the integral of nth power of x is x to the n plus 1 over n plus 1. That works, but we don't want to add any constant there to that rule. And of course, for polynomials, we have n greater than or equal to 0. So starting with a constant, which is a 0 power. In fact, in that case, this could be also then restricted to polynomials with some certain degree, like n degree or n or lower degree polynomials. And of course, we can see that the nth power of x, when we integrate, becomes n plus first power. So that means that the linear transformation goes from Pn to Pn plus 1. We will talk about this later in more details, how important the dimension of the different vector spaces is. And then finally, let's not forget about the matrices, the simplest and more basic linear transformations. If we have an n by n matrix, then we can multiply it with the n by 1 vector, and then the result will be n by 1 vector. So that means that if we define this transformation Ta related to a given matrix A, which is m by n, then the mapping will be from Rn into Rm, with the definition that the effect of the transformation on a vector x equals to ax, a times x, for all x in the Rn space. And then if we want to check the property of linearity, third property can be checked immediately. What we get is that this transformation applied to a1 x1 vector plus a2 x2 vector, for example, that's just a matrix multiplication with the vectors a1 x1 plus a2 x2. And again, from basic properties of matrix vector multiplication, we know that this is a1 times ax1 plus a2 times ax2 vector, which is the same as a1, the t linear transformation applied to x1, plus a2 t applied to x2 vector. We know that multiplying a vector by a matrix is a linear transformation. Let me mention here that we have, for example, the zero matrix with all zero elements, and we know that if you multiply a vector with a zero matrix, you get the zero vector. And also if we have the identity matrix, which is the matrix with ones in the diagonal and zeros elsewhere, then when you multiply a vector with the identity matrix of appropriate size, of course, n by n, then this leaves the vector without any change. So these are similar roles that the general zero transformation and identity transformation play.